So I just want to start by discussing what a brown dwarf is. I've already sort of alluded to it, but the basic idea is that there's stars that we're all familiar with. This is the closest star to us right now, is the sun. And then there's planets. This is the biggest planet we have in the solar system, Jupiter. But out in the galaxy, there's a lot broader spectrum of objects. So these are the brown dwarfs. They sit in between the largest planets that we have and the stars. And so to put things on a mass scale, if the sun is an elephant, brown dwarfs would actually range in size, or mass, I shouldn't say size, so because they're roughly the same size as Jupiter. But in terms of mass, they range from sort of moose, which is about 8% the mass of an elephant, which surprised me at first when I looked that up, but apparently that's correct, and people, human-sized. And then on the same scale, Jupiter would be a small cat. Okay. So it is mass which makes brown dwarfs special, and I'll explain why that is. So this is a cartoon picture of the sun. We're probably all pretty familiar. There's different regions within the sun. A really important region in the sun is the core. The core's main job is to hold up the rest of the sun. It has to create enough gas pressure to make sure that all the rest of the sun doesn't come collapsing down and turn into a black hole or something like that. And so it has to reach extremely high pressures in order to do this. And if you've learned the ideal gas law in school, the only way, for a given volume and density of gas, the way you get more pressure is to turn up the temperature. And so the temperature that corresponds to the pressure that's needed to hold up the sun is about, here it's in Kelvin units, 15 million, that's about 30 million degrees Fahrenheit or so. And at these sort of very high temperatures, there's a nice natural accident that happens, which is hydrogen turns into helium through nuclear fusion, and that allows energy to be generated and maintain this temperature. If that didn't happen, then there would be, the sun would run out of energy and collapse on itself. Okay. So brown dwarfs, on the other hand, are less massive. Right? They don't have to worry about holding up as much mass as the sun does, and so the pressure in their core is much lower because it doesn't have to be high enough to hold up lots of mass. And what that means is the temperature is also much lower. And brown dwarfs, basically, when you become a brown dwarf is when your core is below about 5 million degrees Fahrenheit. Below that temperature, you don't have the gas is not hot enough to have nuclear fusion, and so there is no energy generated. You just gradually, you can still support, the gas can still support the brown dwarf, but as it's radiating away energy at the surface, the brown dwarfs sort of continually contract. They're actually supported a bit by electron degeneracy pressure, and that's why they don't plummet into themselves. They sort of gradually contract over their lifetime. And as that's happening, they're getting cooler. So as I say, they're just losing the energy that they started off with, and they have no way to replace it. And so from the core all the way up to the surface, everything is getting cooler. And so I'll refer to this quite a few times throughout the talk. So as time goes on, the surface temperature of brown dwarfs is getting much lower. And so this is one of the key traits of brown dwarfs and why they end up being pretty interesting objects. And so another consequence of this trait is that they, after having a brief period of time in their youth where they're extremely bright and putting off lots of energy, they actually get cold enough to where they don't put out very much visible light at all. So you can't see them in the visible. Even if you have like a CCD camera on your telescope, it's going to be essentially impossible to find a brown dwarf that you would actually be able to detect with your telescope. We can see them with some of the largest telescopes, but they primarily put off their light in the infrared. And so this is supposed to be a little cartoon to describe what brown dwarfs sort of look like. If we turned off all the lights and all the light sources in this room and shut out all the windows, we wouldn't be able to see each other because our eyes work at wavelengths where we can't detect each other's light. But if we had infrared eyes, we would all be glowing because we all have some heat, and so our faces would be warmer than our clothes and things like that. And so, just for the same reason, brown dwarfs are glowing too. We just don't see them in the visible. And so it was this sort of problem when scientists first started thinking about what to call these objects. there was lots of names being thrown around. I just want to acknowledge the fact that brown dwarf was created in the 70s by Jill Tarter, who is more famous nowadays for being one of the co-founders of the SETI Institute. Some of you may know the character of Ellie Arroway or something in Contact. Jodie Foster's character in Contact was based on Jill Tarter. And you can see Jill Tarter is using the real thing. Jill Tarter is using computers here, not headphones. This is the standard joke. But Jill was interested in brown dwarfs because at the time, astronomers started finding out that there was some missing mass out in the universe. Nowadays, we call this dark matter. It's sort of a well-accepted fact. And so one of the ideas was it could be brown dwarfs because they didn't put out any visible light. And so she wrote her thesis on this stuff, and she proposed this term brown dwarf because, well, they weren't quite red dwarfs, so they weren't stars, but they weren't completely black either. They weren't totally without light. And so brown was sort of somewhere between red and black. And besides, no one really knew what colors they were going to be anyway, so that was it. And of course, nowadays we know actually they do range, since they change so much over their lifetimes, they go through all sorts of different colors and everything. So they're not just one color. The term brown dwarf really just sort of applies to the fact that they're glowing balls of gas that don't have stable energy generation and stable colors and brightnesses throughout their lives. So she was interested mainly in the missing mass, but I think there's all sorts of other interesting things as well about brown dwarfs. So one is, where do they come from? Do they actually form like stars do? Does nature just make them naturally, just like it makes stars like the sun? And if so, how common are they? Are they more common than the sun? Are they less common? And if you could go to them, what would they be like? What kind of worlds are they? Do they look like planets like Jupiter? What sort of things are going on in their atmospheres? And finally, if you think of them as tiny stars, then maybe they have planets themselves, and what would life like be on one of those planets orbiting a brown dwarf? So I'll start off by just discussing where they come from. So do they form like stars or not? This is, of course, they come from the same place that everything, stars and planets, everything we normally think of, everything comes from these star-forming regions. You can see dark regions of cold gas that are blocking out the stars behind this star-forming region. You can see other areas where bright stars have formed and have started ionizing the gas, and so you can see through the gas. So the question is, right, are they forming on their own in these little dark globules of material, or are they forming around stars and somehow getting off out into the universe on their own, or something like that? So to start off with, I'll show you, we obviously don't get to observe stars forming in real time. So to imagine it, we have simulations where we can start with gas simulated in a computer, and we can watch it evolve over millions of years. So that's what I'll show you next. So this is a ball of gas that is allowed to have the normal properties we see in gas clouds in the galaxy, turbulent motions in the interior of the cloud, and these turbulent motions put parcels of gas in contact with each other, and they ram up against each other and create shock waves and radiate away energy, and that, you're spewing energy out and allowing the gas to cool down and form clumps. And once you have allowed enough gravitational energy to escape, these clumps become self-gravitating and they start forming stars, which you can see as these bright dots flying around. And in these simulations, one of the key attributes is that you see stars escaping from the star-forming region. According to these simulations, it's very common for some stars to stay in the nebula and other stars to get ejected through dynamical interactions with the rich environment of stars. For context, this whole movie is only about 3 light years across, so the distance between us and Alpha Centauri or so. So very, very dense environment. We don't live in an environment like this where we live in the galaxy. But when stars are born and when the sun was born, we probably did. So in the simulation, you can't tell different dots apart, obviously, but some of these dots in the simulation turn out to be brown dwarf masses, so they can be very low mass objects, in addition to stars like the sun. So this simulation would say that, sure, we can form brown dwarfs on their own. Now to explore the other aspect, if we look around any one of these stars, they should have a disk of material, protoplanetary disk. This is the sort of thing we think the planets in the solar system formed out of. a flattened gaseous disk with dust in it and planetesimals and that sort of thing. And so now we can ask the question of, what if we look at one of these disks and we allow there to be a lot of gas, more gas than we think was in the actual solar nebula that formed our solar system. But we just turn that up by a factor of 10 or something and see what happens. So here's another simulation coming in from the top. We've zoomed in now on this disk, so there's nice little spiral arms forming. What we're looking at here is the gas in one of these circumstellar disks. And you can see as those spirals form, within them there's little clumps of gas that cool down and become little self-gravitating things. So some of these things will become planets, and some of them would be essentially very, very massive planets. Planets that are 80 times bigger than Jupiter, say. And that would qualify them as a brown dwarf. And yet they formed here in this, this flat disk. Some of them form little binary pairs. And so the question is, is this really the dominant way that we form brown dwarfs, or do they just collapse down on their own and without any help from any star nearby? So to answer that, this just to illustrate this. So the question is whether they collapse on their own. This is an actual image of such a core. This is an image of cold gas detected in radio emission. And this cold gas, we can measure how much mass is there, and it's only about 30 Jupiter masses. So this is something that will become a brown dwarf one day. It's still forming. And then we also sometimes see brown dwarfs around stars like this. So the question is, which of these two modes is more common? And so first, I guess I should step back for a moment and describe how we find brown dwarfs. So it's probably no surprise that the key way, and I guess I've already kind of alluded to it, is using infrared cameras to do this. So nowadays, this is very common. Most of you probably in this room realize that you can go out and buy infrared goggles or whatever. When Jill Tarter was doing her thesis, I don't think there was maybe 1 pixel infrared cameras, and now we have infrared cameras that have as many pixels as CCD cameras do in the visible. And so it's really been, over the course of my lifetime, technology has developed such that we can now survey the sky in infrared wavelengths in ways that we hadn't been able to before. So one of the first big surveys to do this was the 2-micron all-sky survey. So it's called 2 microns because that's the wavelength that it's observing at. For reference, our eyeballs sort of see 0.3 to 0.9 microns or so. So it's a little bit further in the red than our eyeballs see. And this is a map of the entire sky. So you can obviously see the Milky Way very prominently in the center. The Large Magellanic Cloud is sort of down to the right here, a Small Magellanic Cloud. And you can also see just lots and lots of stars. And so 2-micron all-sky survey, or 2MASS, as people like me call it, 2MASS created this great infrared atlas of stars. And this is how some of the first brown dwarfs were discovered. And very recently, this has been complemented. We've gone even deeper and found even colder brown dwarfs by doing this sort of survey in space. So this was done from the ground. But the problem is, if you go farther out to longer wavelengths than this, the sky starts to glow. Your telescope starts to glow, just like the picture of the people sitting in the room. If your telescope is glowing, it's going to be very, very hard to see faint things in the sky, and if the sky is glowing. So the way you get around that is you go to space, you put a satellite that orbits the Earth. There was a satellite called the Wide Field Infrared Survey Explorer. It was in a polar orbit around the Earth, so it was going over the South Pole and the North Pole. And so by doing that, over 6 months, it was able to map the entire sky at longer infrared wavelengths than we had done before. And so this allowed us to probe even deeper and see really the coldest brown dwarfs that are in the solar neighborhood, the area that's right in our little neighborhood of the galaxy. And so this was only a few years ago. And so now I'll show you what we know about our neighborhood now. So here is a little rotating movie of just the volume of, if you look out in 32 light years in every direction around the sun, what do you find? And every little dot here is a star or a brown dwarf. The ones with numbers next to them are, I believe, binary or various. If it's got a 2, it's a binary system. If it's got a P next to the number, then it's got some planets, got some extrasolar planets. But the important thing here is just to know that we have a nice census of everything that's in our neighborhood. And now we've pushed it down far enough to see where all the brown dwarfs are as well. So now we can ask the question, how common are brown dwarfs free-floating on their own when we look around us? And so here's what happens if you just count up the number of different types of objects. Here they're broken down into spectral types. You don't really have to worry about that, but one of these bins is sort of sun-like stars. The one down here are the brown dwarfs. This really big one are the M dwarfs, or the red dwarfs. They're kind of the most common stars in the galaxy. And so what you see here basically is that stars in the galaxy follow essentially what's a bell curve, or a Gaussian distribution. So it's the same sort of bell curve that there's really intelligent people, there's sort of average intelligent people, and there's only a few people who really bomb the SAT, which is what this plot is showing. I won't tell you where my SAT score is, but according to this, I probably wouldn't have gotten into Harvard. So, so we can do the same thing for stars. And the bell curve for stars looks something like this. The sun is actually a little bit above average. Red dwarfs are really, really common. Red dwarfs are smaller than the sun. So the sun's on the high side of the distribution. But brown dwarfs are way down here on the really uncommon side of things. And so I can also show you, this is another way of looking at this. Inside this box are all those stars from the previous little rotating movie. And here are the brown dwarfs that are in that same volume of space. So if you count up all these stars and you count up the brown dwarfs, what you see is that there are about 25 stars for every brown dwarf. So we can go back to this question of how often do brown dwarf stars form on their own. And it looks like roughly that rate is about 25 to 1 compared to sun-like stars. So then we can ask, there's been other surveys that have gone out and looked around all the stars that are near us to see if there's any brown dwarfs around them. We can ask how often does that happen, and that answer is about 100 to 1. So it turns out brown dwarfs are much more common to be found free-floating on their own in the galaxy than they are bound to another star. And so some people will still actually debate about this. I've given you my perspective. Some people will say, well, the ones that are free-floating actually started out around stars, but they got ejected. And if you remember from that movie I showed you, the blue movie, there were some little brown dwarfs that got thrown out. But my opinion is that the evidence shows that they probably formed more like stars. And when they do that, they're pretty uncommon outcomes of star formation. So what do these sort of rare, small things look like if you could actually go there? Well, as I mentioned before, they're always cooling down. So what they look like will depend on what age you happen to be looking at of the object. But let's just do a comparison between, on the left, what's called a mature brown dwarf. I guess they don't like to be called old. And then Jupiter's on the right, which Jupiter would be a mature giant planet, 5 billion years old or so. So I should say the dotted line here that's horizontal, that's essentially what we would call the surface. That's what, if you went to that object and you looked at it, things above that line are things you would see with your eyes or with the telescope, and things below it would be sort of hidden from view, but they would be there if you could actually probe down into the atmosphere. So of course, neither of these things have a rocky surface. We don't know if Jupiter has a core or not, and we're not even looking that low down. So for the brown dwarf, you have above the surface, you have a mixture of methane and carbon monoxide. So carbon monoxide is the toxic gas that you're not supposed to run your car in your garage with the door closed. Sulfides are basically, I think they're basically the stuff that rotten eggs smell like. That's what makes rotten eggs smell bad. Those would be sulfides. And there would be sulfide clouds in this brown dwarf above the surface. And then just below the surface, you would actually have clouds of various silicates. So magnesium silicates include things like talc. Trying to think, there's some other, like peridot, I think, is a magnesium silicate. And then you have this iron rain. So you have liquid iron droplets. And so you could imagine some sort of iron hydrological cycle, but with iron. And then below that, you have more minerals and things. This is what brown dwarfs. They have lots of mineral clouds. So corundum. Does anyone know what crystallized corundum is normally called? Ruby. That's right. That's one of them. Sapphires also. It depends on what impurities are in it. But so you can have clouds of ruby, sapphire type stuff, except they're not in crystalline form. So you have to cool it down. So in comparison, Jupiter essentially shows some of the same traits, but the sulfide clouds are way below the surface, and then it's even cooler at its surface, and so you get clouds of ammonia and water, and then above that, it's mostly methane, and there's a little bit of carbon dioxide. And then in both of these objects, there's actually some mixing that's going on. In Jupiter, it's all below the surface. We don't see a lot of the mixing right where we can see it on the surface. But in the brown dwarfs, actually, it's expected that there's actually convective motions bringing up, and this is why you get carbon dioxide above the surface of brown dwarfs. You get this hot gas coming from below and coming above the surface, and everything sort of gets mixed all together. So now I'll compare a brown dwarf to an object of the same temperature. So this would be an old, massive brown dwarf compared to a younger, lower mass giant planet, still several times the size of Jupiter. And you can see essentially it's a similar thing. Some of the clouds that are below the surface for the brown dwarf are higher up in the atmosphere for the planet. And so one of the things I think is interesting about this is, both of these slides sort of highlight the fact that brown dwarfs and planets have a lot of the same sort of cloud stuff going on. They both have mixing, but but things vary depending on whether you look at different temperatures and at different masses. So let's go back to the surface. This is what the surface of Jupiter looks like if you look in the thermal infrared, so this sort of long wavelengths I was talking about, going to space to see. And so what you see here, the main thing you see, right, these bands. So you see bands in the clouds of Jupiter when you look at it, from ground-based telescope through the eyepiece. But in the infrared, you see the same thing, and what the darker regions will correspond to essentially thick cloud decks that are blocking our view of the deeper, hotter gas that's inside the planet. This little circle with the dot on it actually shows you where the Galileo space probe, flew into Jupiter and ended its life. Actually happened to be in one of these hot spots. So it went through a fairly cloud-free region and went straight into the hot gas interior. So, and it just so happens this image does not include the Great Red Spot. So to show you that, here's a thermal image of the Great Red Spot on Jupiter. And so, as you might expect, the Great Red Spot is a great storm. And so that storm is made of these thick, high cloud decks. And so the red spot is actually very dark in the infrared because of that, because it's blocking our view. So what if we went to people have started looking at brown dwarfs to see if they vary in brightness. So if brown dwarfs had great storms like the red spot, what you might see is you would see this dark storm region come across and cause the light from the brown dwarf to dim a little bit, and then the storm would go back on the other side of the brown dwarf as it rotates, and then the brown dwarf would get a little bit brighter. And the expectation was that if you had something like the Great Red Spot, it's about 1% the surface of Jupiter, so you would only see variations in brightness by about 1%. And for a long time, people couldn't find any variations, but that 1% is pretty hard to do for brown dwarfs. But recently, people have started finding brown dwarfs that are varying by 10 times that. And so there are some brown dwarfs that we know of now that may look something more like this, where there's a really huge storm on the surface that's covering a very large fraction of the surface of the brown dwarf, with just incredibly high winds or all sorts of other things going on. And so in some of the brown dwarfs we know now may have great red spots that are 10 times bigger than the ones that we see on Jupiter, but not all of the brown dwarfs. So if we do see storms on brown dwarfs, what else might we see? Well, some people have started playing with models and finding that they actually see electrostatic, discharges within the atmospheres of brown dwarfs, implying that there's actually could be these energetic lightning-type events happening inside the brown dwarf. And so if you're familiar with the Miller-Urey experiment way back, that basically showed if you had some basic molecules lying around and you just zapped it with electricity, you could create the building blocks of life. And this was sort of one of the early explanations for how the young Earth was able to get things like amino acids seemingly out of nowhere. And so there's now this suggestion floating around that maybe inside the atmospheres of brown dwarfs you have all sorts of molecules available to you, molecules and different types of minerals. And so you could potentially create all sorts of different types of complex organic molecules like amino acids if there's these sort of lightning storms happening. And so this reminds me of the concept of life in Jupiter. Carl Sagan had proposed the idea that you don't really need a rocky surface to have life. We like to think of that, but you could have things floating around in the atmosphere, provided you had the right ingredients to create such creatures, right? And so it may be the case that brown dwarfs could have, if they have the ingredients for life within them, you could have things floating around living there. But what about normal type of life? This is another artist's conception of what it'd be like to be on a rocky world, with a nice liquid water lake, water you could actually drink, but instead of having a sun, you'd have this it would be big in your sky because you'd have to be close enough to it to have liquid water. Big brown dwarf as your sun instead. Well, when we look at young brown dwarfs, we see plenty of evidence that they have disks, these flat disks, like I was referring to earlier, with lots of gas and rocks floating around. People have detected millimeter-sized particles inside brown dwarf disks. And so there's no reason to think that brown dwarfs don't have the building blocks of planets as they're forming. And this goes along with the idea that brown dwarfs form just like stars. It's just that they never quite get enough mass to have fusion. So if you want to have life around a star, there's this concept of the habitable zone. We're in it, obviously, the Earth is. We're just right. We're not so hot that all the oceans boil off the surface and escape, and we're not so cold that all the water is locked up into ice, like you see in the some of the moons around the outer planets. There's plenty of ice there, but there's not a lot of liquid water, except perhaps under the subsurface oceans of maybe Europa and some of the other satellites. But in terms of having liquid water on the surface, this is what scientists, astronomers, this is what we know that life can exist under these conditions. So this is what we often think about when we talk about habitability. So here's the thing, right? Stars are different sizes, different temperatures. More massive, brighter stars, the habitable zone will be farther away because you don't want to get too close to it because it's too hot. The really much smaller stars you have to huddle up closer to in order to get the warmth that you need to keep water liquid. So what this means is that the habitable zone around something like a brown dwarf will be exponentially closer to the surface of the brown dwarf than we are from the sun. So just to give you an idea, so for sort of typical temperatures for brown dwarfs, as brown dwarfs get older, a young brown dwarf, you might want to be 1 million miles away from the surface in order to be the right temperature. But then 1 billion years later, you'd need to move closer. You need to be only 300,000 miles away. And then, toward the end of the brown, or I shouldn't say the end of its life, it'll live forever. But several billion years in the future, you'd want to be only 80,000 miles away. So 80,000 miles is pretty close. To put things in perspective, does anybody know how far away the moon is in miles? Yeah, 200,000 miles. I always remember that because my a physics professor I had in college told me that's how many miles he got out of some car that he owned. So that's roughly the right distance to the moon. So you're talking about you need to be closer to this brown dwarf surface than the moon is to the Earth in order to actually gather the heat. But that's not the problem. I'll explain. There's actually a bigger problem here. And that is that if we imagine a nice, cozy, habitable planet today around a brown dwarf that is, let's just say it's roughly the same age as the solar system, what if we look back 2 billion years ago? Well, the brown dwarf was younger, it was hotter, brighter, and so the habitable zone was a little further away. This planet would be right near the edge. Now, the Earth in the solar system actually happens to be near the edge of, depending on how you compute the habitable zone, some people will tell you the Earth is pretty close to the inner edge, so maybe this is okay. But then if you go back to the beginning of its life, this planet would have been toasted so much that it wouldn't be able to retain any water on its surface. And so really what you see today, there'd be no way to actually have liquid on the surface because it would have undergone this epoch in the past of intense radiation from the brown dwarf. And so this is why it's very hard to imagine there being habitable planets around brown dwarfs. You basically have to move your planets around within the system, which if you're just trying to get life started, which can take 1 billion years. On the Earth, it took 1 billion years before we saw any signs of life on the Earth, and then another 3 billion years or so until you got the life that sort of we think of, the sort of swimming, crawling, flying life. But even just getting single-celled organisms took a long time. And so life has to evolve really, really rapidly on brown dwarfs if it's going to exist, and then it's going to have to move. So that is basically a lot of the stuff that I find really interesting about these objects. They seem to be made by nature, very small. Nature puts them out in the galaxy with no way to really fend for themselves or provide for themselves, and so they just go colder and fainter over time. Of course, nature doesn't do that very often. These types of objects are actually fairly rare in the galaxy. But if you could visit them, they might not be very friendly to our type of life. The atmosphere is full of all sorts of poisonous gas, and you probably wouldn't want to be breathing in minerals either, and possibly extremely stormy, with storms that are 10 times bigger than you see on Jupiter in the Great Red Spot. And the life there would have a really hard time forming and existing long enough to get to the point where they could talk to us or something like that. Thanks.